Welcome to the talk of the paper Expressive Power of Linear Algebra Query Languages. I am Cristian Riveros, and this is a joint work with Floris Gertz, Tomás Muñoz, and Domagoj Borgoch. Linear algebra is everywhere today. We can find it in database management systems, like in database learning, and also in programming languages like MATLAB, R, etc. Basically, linear algebra is a basic tool of every data scientist today. So the question here is, what is a suitable query language for linear algebra? For this, there is a recent proposal that is called MATLAB, which is a query language for matrices. This paper was proposed in the paper on the expressive power of query languages for matrices in ICDT 18. And this language offers these operations like matrix variable, transpose, one vector, diagonalization, etc. MATLAB includes the basic operations for managing matrices. The problem of MATLAB is that its expressive power is very limited, and it's included in first-order logic with 3 variables. In particular, it cannot define for click, inverse, determinant, etc. So MATLAB is included in FO3, and outside we have several linear algebra operations like determinant and inverse. To solve this, people has extend MATLAB with determinant or extend MATLAB with inverse, but it's difficult to understand what is the expressive power of these extensions. So, can we extend MATLAB with natural operations for capturing linear algebra? Here comes for loops into play. For loops are very useful in linear algebra algorithms and basic blocks in all matrix programming languages. As an example, for computing the transitive closure of a graph, we can see that by using the Floyd-Warshall algorithm, this works like a sequence of nested loops that runs from 1 to the dimension of the matrix to represent the graph. So our contribution in the paper is first to introduce for MATLAB, which is an extension of MATLAB with for loops. Second, we showed that for MATLAB has the same expressive power as uniform families of arithmetic circuits. And third, we defined subclasses of for MATLAB that capture relational algebra over key relations, among others. This is a talk too short. Please see the paper for more details. I will give a brief overview of the first and second point. For MATLAB in 1 minute. So this is the syntax of for MATLAB that includes several operators of MATLAB, and it extends with this for loop operator that we have at the end. So this for loop clause has 3 parameters or 3 variables. First, v is a vector or variable vector of dimension n. Second, zeta is a matrix variable that has dimension n and m. And finally, e is an expression that can include v and zeta and has the same dimension as the zeta variable. To define the semantics of this operator, we need the basic vectors of dimension n, b1, b2, until bn. And the semantics of the for loops is given as follows. Suppose that we want to evaluate this for loop expression. For this, we start with zeta 0, that is the 0 matrix. And then we define zeta 1 by using zeta 0 and the first vector. Basically, we evaluate e over the first basis vector and zeta 0. Then we evaluate zeta 2 by evaluating e over b2 and zeta 1. And so on until we reach zeta n, which is the evaluation of e with bn and zeta n minus 1. Finally, the semantics of the for loop operator is given by the last matrix zeta n. To give an example, suppose that I want to evaluate the formula that is on the left that is a for loop over this expression of zeta plus b multiplied by a and multiplied by b, and the matrix on the right. So we start with the zero matrix, zeta 0, and then we evaluate zeta 1, which is the formula, inner formula evaluated with zeta 0 and the first basis vector, which is this computation that we have to do here. And if we do the math, we can see that is this matrix with 2 on the corner. Then we evaluate zeta 2 by using zeta 1 and the second basis vector, and we need to do these math operations that are here, and we finally get the second matrix, that is zeta 2, that has 2 and 3 in the diagonal. Then we continue with zeta 3 with the same idea by using zeta 2 and the third vector. We have to do this math, and finally we see this result of this matrix. So the semantics of this expression is the zeta 3 matrix, and we can see that these expressions compute the diagonal of a matrix. ForMATLAN can define common linear algebra operations. In the paper, we show that we can compute, for example, the LU decomposition of a matrix, that is the Gaussian elimination, also the inverse and the determinant of a matrix. So we can do several linear algebra operations, and the question is if does ForMATLAN capture linear algebra or not. So basically, what is linear algebra? What can we say about this? And here we have two arguments. First, several problems like determinant or inverse have been shown to be definable with families of arithmetic circuits of low depth. And second, several operations in linear algebra are highly parallelizable, like by using arithmetic circuits or similar models. So in the paper, we use arithmetic circuits as a yardstick for linear algebra expressiveness. So what is an arithmetic circuit? Basically, an arithmetic circuit is the same as a Boolean circuit, but instead of Boolean gates, we have arithmetic gates that are plus and product gates. We also have input gates that receive real values. Then, when we receive the input, the real values, we compute the operations to the top, and the top gates basically output the evaluation of these gates that basically define a polynomial. We care here in the paper about uniform families of arithmetic circuits that are given by a log-space transducer. The machine receives as input the size of a circuit, and it outputs the circuit of that size. Where with size we mean the number of input gates. Here, the log-space transducer always produces circuits of polynomial size, and we also restrict these families to have logarithmic depth. That means the height of the circuit has to be of logarithmic size with respect to the number of gates. Then the first theorem of the paper says that from circuits to ForMATLAN, we can show that for any uniform family of arithmetic circuits of logarithmic depth, there is a ForMATLAN expression E that computes the same result. This is the most technical result of the paper, and the proof idea has two main ideas. The first one, given a log-space transducer, we can build a ForMATLAN expression that simulates this machine. Second, we need to show how to evaluate a circuit, and for this, what we do is a depth first search traversal of the graph by using two stacks, one that keeps the gate IDs and a second stack that keeps the partial values encoded in a matrix variable set. We can extend this result by considering the degree of the family, and we say that a circuit family has polynomial degree if the degree is bounded by a polynomial. Then we use a result from Valiant et al. That says that any function computed by a uniform family of arithmetic circuits of polynomial degree can also be computed by a uniform family of arithmetic circuits of logarithmic depth. By combining this result of Valiant and the previous result, we can show that for any function f computed by a uniform family of arithmetic circuits of polynomial degree, there is an equivalent Fermat-Lang expression. Finally, we can show the other direction, going from Fermat-Lang to arithmetic circuits, and we can show that for any Fermat-Lang expression E, there exists a uniform family of arithmetic circuit that is equivalent to E. So as a corollary, we showed that uniform families of arithmetic circuits of polynomial degree are equivalent to Fermat-Lang expressions of polynomial degree. So in some sense, we can say that the expressive power of Fermat-Lang captures linear algebra. Finally, some conclusions. In this paper, we show that Fermat-Lang captures the expressiveness of arithmetic circuits, and also we show that subfragments of Fermat-Lang capture different logics over matrices. About future work, it remains to understand the expressive power of some subfragments of Fermat-Lang, and also it will be interesting to understand some query optimization of Fermat-Lang or its subfragments. Thanks for hearing me, and I will be there to answer questions. Thanks.